Multiple loop circuits. This is a multiple loop circuits. How many loops we have? This is one loop. This is one loop. Also, we have another loop, this big one. Okay, it looks like we have 3 loops, but actually, later on, you know, only 2 are independent. More than one junction. The judgment, what is the multiple loops? What is junction? Junction is more than 2 branches, at least 3, meet together at the junction. And that's B, 1, 2, 3. 1, 2, 3. So B and D are junctions. And A and C are not, because only 2. Okay, 2 branches is not a junction. Okay. Sigma I in equal to sigma I out, with the charge conserved. So the current get into the junction equal to current get out of the junction. No current, no charges from the junction or into the junction. Now, we choose the direction of the current arbitrarily, any loop. In this case, we choose I1, I2, I3. Okay.
The amount of current entering a circuit junction or node must equal the amount of current leaving the node. We'll use this setup of batteries, resistors, and ammeters to show that is true. The ammeters are set up to read the current flowing into and out of this circuit node. Here are the currents at the node at the first resistor setting. The total current flowing into the node is equal to the total current flowing out. Here are the currents flowing into and out of the node after the values of the resistors are changed.
Junction rule. The sum of the currents entering any junction must be equal to the sum of currents leaving that junction. This rule is often called Kirchhoff's junction rule or Kirchhoff's current law. The number of independent equations, including the number of junctions minus 1, because they are independent. 1 is not, so you total number of junctions minus 1. Plus the numbers of independent loops. Each loops we can write an equation. And these put together should equal to the number of the unknown currents. This is the rule. An independent loop must contain a new resistor or battery, at least, which has not been counted before. If they did, then it is not independent loops. Okay, then we do this one. This is multi-loops. How many loops? 1, 2, and big one, 3. Okay. How many junctions? Now, 1 junction, 2 junction. So we write the equation for current 2 minus 1, 1 junction. For example, we take D. If you take D, okay, I1, I3 flow in, I2 flow out. So we have I1 plus I3 flow in equal to I2 flow out. How about this one? Okay, a junction B, if we write another equation, is exactly equivalent to this equation. So only 1 independent. Circle, we can have 1, 2, 3. Let me see that. We can circle B, A, D, B, this one. We start from here, okay. Epsilon 1 plus minus I1 R1 plus I3 R3 gotta be equal to 0. And another one, okay, B and B, D, C, B, this direction. So from here is minus R3, R3, minus I2, R2, minus epsilon 2 is 0. That's a three equation, okay? This equation have three unknown, I1, I2, I3. Principle we can solve in mathematics. You have asked question, how about the big loop? Of course, it's a loop. But they look at big loop, R1, R2, epsilon 1, epsilon, all has been counted before. So new stuff, no new stuff. So it's not independent. So in this case, we have three equations. Of course, if we don't count this one, we count this one. Second, we have these two, a new one. It's independent. Okay. Anyway, in this way, we have three equations and three unknown. This is a tedious work from high school. Okay, so we can solve it. Okay. Now, this is the answer again. Now, let me give you something. Physics. Suppose I3 is infinity. We cut this one. What happened? Look at this one. You have I3 is infinity. I3 is infinity. Okay? All right? And so this can drop because compared to have I3. So on top is epsilon 1 minus epsilon 2 R3 divided by okay, I2 plus I1. Forget about this. Okay? And I2, I3 drop this one. I3 drop this one. We get I2 equivalent to I1. And look at this one. This one is I3 is in denominator. So this is a 0. We get I3 equal to 0. I1 equal to R1. This is exact situation, right? Yeah. If they cut this one, of course I3 equal to 0. I1 equal to I2. Okay. Sample. This is another multiple loops circuit. Pictures a circuit whose elements have the following values. Epsilon 1, 3.0 volt, epsilon 1. Epsilon 2 equals 6.0 volt, epsilon 2, epsilon 2. R1 equal to 2.0 ohm, R1, 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 R1. R2, 4.0 ohm. The three batteries are ideal battery without internal resistance. Find the magnitude and the direction of the current in each of three branches. So 1, 2, 3. First, we assume the current arbitrarily. Now here was when assume arbitrarily. Okay. This is I1. This is I1. This is I3. In between is I2. Then we study from this one. How many loops we have? 3. 1, 2, and big 3. Okay. First, we take junction. How many junctions we have? Junction is 3 branches, A and B. Okay. So we write the equation for currents is 2 minus 1 at point A. Which is when I3 in, I1, I2 out. So I3 equal to I1 plus I2. No more equation for current because only 2. The n minus 1 is independent. 2 minus 1 equal to 1 is independent. Only 1. Then you create the loop. Okay. The loop, we go the clockwise. Go this direction. So A minus I1 R1 minus epsilon 1 minus IR1, go ahead, plus epsilon 2 plus I2 R2 equals 0. And then we go this direction. Okay, the clockwise, which is plus I3 R1 minus epsilon 2 plus I3 R1 got this, plus epsilon 2 plus I2 R2 equal to 0. Now, how about this loop? In this loop, all the resistance of battery has been counted, so nothing new. So it's not an independent loop. 3 unknown, I1, R2, R3, 3 equation. So we can solve this one. This is a tedious work. I'll just give you the answer. Okay, we get I1, I2, 3. We look at this one. I2 is a minus number. That means the real current goes this direction. Okay. The ammeter and voltmeter. Okay. Voltmeter is measure potential difference. Okay. It automatic potential difference and avoid to interfere the current. So it's connect parallel, and the resistance should be much larger than R1. In that case, we can reduce the interference because of this connection. The current goes this direction. Okay. Ammeter, we measure the current, so it should connect in series. Okay. Okay. And in order to avoid to interfere that measurement, the R resistance, internal resistance ammeter must be very small. Okay. Ohmmeter can measure the resistance. Okay. And we have multimeter, so you can measure the ampere, voltmeter, and ohmmeter.
This galvanometer will be used to show the electrical connections that change a galvanometer into an ammeter and a voltmeter. Running a 25 milliamp current through the galvanometer drives it to full scale. If we want to measure larger currents, we must connect a shunt across the ammeter like this. The reading now goes nearly to 0 because the meter now requires 1 amp to go to full-scale deflection. If we increase the current, we again get a reading. To measure voltage, we connect a specific resistance in series with the galvanometer like this. Now we have a 10-volt full-scale voltmeter, which we can use to measure the voltage of this 1.5-volt battery. A 6-volt battery produces a larger deflection. We'll use these 2 voltmeters to demonstrate what happens when a voltmeter of low resistance is used to measure voltage on a high resistance circuit. These 2 potentiometers are hooked in series with a battery, and the voltage across one of them is measured with this electronic voltmeter, which has a very high resistance. When this voltmeter with a lower resistance is hooked up to measure the same voltage, it reduces the voltage it is supposed to be measuring.